Hello and welcome. I hope you are having a great day. In this video, we are going to understand vector norms. Very important topic. Okay, so let's understand. So let's set up the agenda first. What is? So we'll understand vector norms and also we'll discuss matrix norms. And within matrix norms, we'll discuss what is Frobenius norm and then we'll discuss vector induced norms. I'll explain each and every term. Okay, so let's go with the first thing. What is a norm? Here in context of vectors, what is a norm? What is a norm of a vector? So norm is nothing but it is in simple terms it just tells you how big a vector is. It's a way to measure the length of the vector, or how far the vector is from the origin. The total length from the origin, and there are different ways to measure that, and that's what we'll understand in this video for vectors as well as matrices. Okay, so what is it? Vector is nothing but it's a way to measure how big a vector is. It's a way to measure how big a vector is, or you can say how far it is from the origin, distance from origin. So this is what it means in simple terms, and mathematically speaking, it is a function that maps an n-dimensional vector to a scalar. It is a function that maps a vector function. It's a function f that maps a vector which is an n-dimensional vector n cross 1 to a scalar that is a real number, that is 1. So it is a function that maps a vector which is n-dimensional to a real number or scalar. So this is mapping from real number to scalar. So this is a vector, this is scalar. So that is what it does. You give an input as a vector, and the output that you get is one real number, a scalar, and that is a length, magnitude, or distance from the origin, or how big a vector is. I hope that's clear. So in order to calculate the norm, so there are some rules the way we define a norm, that to qualify as a norm, if you have some formula, it should follow these. There are three important rules that it should follow. That has been defined. So there are three rules that norm should follow. So what are those rules? So the first rule is that the norm of a vector should be greater than or equal to 0. It should never be negative. It should be never negative. It should be greater, because it is a measure of size, right? Magnitude. So it should never be negative. We don't have size as negative. So that's something, and it will be greater than or equal to 0. And this will be equal to 0 if and only if it's a 0 vector. It's a 0 vector. 0 vector means a 0 size vector. So this can be 0. The norm of a vector can be 0 only if it's a 0 vector. That's rule number 1. Rule number 2 is that if you scale it by a scalar, then the norm should scale by that magnitude. If you write it formula wise, then if you multiply a vector by a scalar, then all the terms will be multiplied by that term alpha, right? That's how it is. So this norm should be equal to only if you take the magnitude and then the norm. So the way to represent norm is a double line, and that's what the function, I'll write it here also. So the function here, this function, let me write a symbol. So it is denoted like this. It is this function, a double lines, and then you write the variable in the middle. It maps our n-dimensional vector to a scalar. It is given by double lines. Whenever you see, you will see many places there are double lines around the vector. So this means this is a length or norm of vector. That's clear. So this is what it should be. So this is only the absolute value, because first rule, it will always be positive. Then the third rule is that it should follow a triangle law of inequality. So generally, in a triangle, right, sum of two sides is greater than the third side. That's what even these should follow. So if there are two vectors, norm of these two vectors should be less than or equal to the individual norms. So sum of two sides is greater than the third side. So this is the triangle law of inequality. If we have individual norms, and if I add them, and if I have a vector which is sum, okay, so the max it could be like they can both be equal, but otherwise if you add those two, the net length will be less than the individual lengths summed up together. This is what it means. So these are norm, okay, it is a formula, it is a function which maps a vector to a scalar, which gives me the size or how big it is or how far it is from origin, and should follow 3 rules. So this is a norm in nutshell, right? So there are, so norms has some more terms. So there are like p norm, okay, there's a p norm, it is generalized form of the formula for a norm, okay, or the equation or this function. So that is called generalized form is p norm. So that is the most common family. There are multiple families of vector norms. This is the most common family of vector norm. Most common family of vector norms. And what is the function? So the p norm of a vector is given by summation I equal to 1 to n xi, magnitude of xi to the power p, and this whole to the power 1 by p. This is a generalized p norm. So any that p can be like equal to 1, 2, 3, n like that, right? So this is the placeholder for that. So what power of the norm we are dealing with? So maybe say if p is power, right? So what power of norm we want? So that is a generalized form. So let's get specific, and we can change the value of this p. We can put here as 1, 2, 3, and the corresponding changes, and then we will get different norms. So let's see the norms that we know already, and now you will get the understanding. So there is something called L1 norm. So this is where p is 1. Here p is equal to, I'll write here itself. So if you put p is equal to 1, you will get L1 norm. That is called L1, length 1 norm. So the formula, just apply, just put p in this formula, and you will get the first norm, L1 norm. This is called L1 norm. Okay, this is equal to sigma I equal to 1 to n mod of xi, just mod I, because this is 1 and then to the power 1, so that's redundant. So we just give this. So this is equal to what it will be. This will be like distance mod of x1, all the entries of, okay, if x is a vector, say for example if x is a vector, right? So this will be x1, x2 like this till xn. This will be n cross 1 vector. So this L1 norm is nothing but the absolute values of these each individual scalars, and you just sum them up, even if it's plus minus whatever. Finally you get the individual absolute values and sum them up. This is this has also got another name. It is also called Manhattan distance. This is because the name has come from the city of Manhattan, where all the streets are at right angles. If you go to Manhattan, all the streets, okay, are at right angles. So you can, if you have to go from any place to any place, you can just go at 90 degrees. You cannot go like this because there will be buildings in the middle. So you will have to, if you have to go to some place, you will have to take that 90-degree distance this way or this way, if these are the routes. So that's why it's called Manhattan distance also. Okay, so that is the case. So then the next one, more common one that you know, that is most frequently used, that is L2 norm. When you put p is equal to 2, is the most familiar, you must be aware of this. Okay, so this is denoted as x2, you must have seen this. Okay, and this is equal to sigma I equal to 1 to n. Now the mod of the distance xi whole square power half. Now I have substituted p with 2, so now this will come. So p I have put as 2 and then power half. This p here, this is square, this will half. That's what it is. And if you see, this is nothing but summation of, this is half is a square root, and each one is like a x1 square, x2 square, like this till xn square. Do we know something like this? This is nothing but your Euclidean distance. In the coordinate geometry, that's the Euclidean distance, right? This is nothing also called Euclidean distance. Say for example, let's do simply. Say for example, this is your coordinate axis. Okay, you have 1, 2, 3, 4, 5 like that. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. This is 0, 2, 3, 4, 5. So say if you have vector 3, 4, okay, something like this. X is 3, y is 4. Something like this. So this is a vector x3, y4. So what will be its Euclidean distance? So x is 3, y is 4. Okay, so this distance is 4 units, and this is 3. So what will be its L2 norm? So if this vector is v, so the L2 norm would be square root of 3 square plus 4 square, that is equal to 5. And what will be the L1 norm? This is your Euclidean distance. What will be the Manhattan distance for this? This will simply be right angles. You travel only one axis at a time. Okay, towards one axis. You are just moving in the shortest distance here, right? Both the axes. Here in Manhattan distance, you just move towards one axis, and once you have hit there, then you move perpendicular to that. That's why you cannot move across two axes. So you move towards one axis, and when you come, you have to turn at right angles. So this is your Manhattan distance. So this will be your absolute value of 3 plus absolute value of 4. This is equal to 7, and this is your Manhattan distance. Distance. I hope now this is clear. Okay, so this is L1 and L2 norm. The L2 is the most common, and then we have something called, okay, we'll continue this example, and then we will, there's one more norm. Okay, so there's one L infinity. So there's one L infinity norm where E is equal to infinite dimensions. So this is here. How do we write it? X infinity, this is equal to limit p tends to infinity, sigma I equal to 1 to n, and then the mod xi to the power p whole to the power 1 by p, and we put limit p tends to infinity. So what will be this? This turns out to be, if you solve it, this will come as max value of xi. Max value of absolute value of xi, because it's distance, so always it will be positive, so that's why we put this absolute value. Okay, so for the same example, this 3, 4, what will be the L infinity norm? So for the same vector, what will be v of infinity? That will be max of 3, 4, that is equal to 4. So this is L infinity norm for this vector itself. So for the same vector, you had 3 different values. So L1 norm was 7, that was a Manhattan distance. L2 norm was 5, that is a Euclidean distance, and the L infinity norm was just 4. Okay, so this is your vector norm. I hope this is clear, and this is how you measure the distance, or how big a vector is, or how far it is from the origin. Okay, so for example, if I sum all the vector elements, here I have these vector elements, right? So if I take a norm which is defined as sum of all the vector elements, can we take that as a norm? Yes or no? No, right? Because this sum, if there are positive and negative values here, like they can be towards negative axis also. If they're positive and negative, if the net value comes out to be negative, then it won't fulfill this criteria, right? The value should always be greater than 0. So just taking the simple sum of all the entries cannot be taken as a norm. So that's the reason I'm telling you, because it's a distance. So that is one thing to consider. Why are these rules important? Because distance cannot be negative. That's why you have these rules. Okay, so let's now move to matrix norms. So even a matrix is nothing but collection of vectors. So vector is one dimensional, matrix is two dimensional. Vector norms, sorry, matrix norms. So what is a matrix norm? So there are, okay, so again this is a function. I want a function that will give the give me information about how big the matrix is, the size of the matrix. Size means in terms of length. Okay, if it can give me a measure of that. For vector we can understand physically, but even we'll deal with the matrices. So even for that we may need this unit to compare two matrices in context of their size, okay, or how big it is. And for that we have a matrix norm defined, and let's see how. So it is a function, okay, function, say for example function f, which is defined like this, okay, which maps a matrix m cross n to a scalar value. So finally it will give me a measure of distance. So a matrix can be m cross n, and finally I'll get a scalar which will give me the length or how big this matrix is in terms of size. Okay, and it should satisfy all the three properties. Okay, it must satisfy all the three properties that we discussed above for vectors. That means these three, that it cannot be non-negative, okay, and the scaling factor, if I scale it by alpha, all the entries, then it will scale by alpha, and the triangle law of inequality, it should follow all these rules. Even the matrix, all the norms, any kind of norm should follow all the rules. So even matrix norm will follow these rules. And there are two types, okay, so these are of two types as I mentioned. First one is the element wise norm. So I have m cross n elements, it's a grid element wise norm. In that we will discuss the Frobenius norm. It's a name of a mathematician, I understand. And the second one is vector induced. Okay, vector induced means when I multiply a matrix with a vector, so it gives me the linear transformation the matrix does on the vector, and then depending upon that transformation or change in the size that has been incurred on the vector because of the matrix by being multiplied by that matrix, so we measure that change in size, and that's what is captured in vector induced norms. There are two types, so we'll go one by one. Vector induced norms. So first one is element wise norms. That is simple. So element wise norm, this is, you will see this a lot in many research paper. Frobenius norm, it is given as like this. Say for example this x is there, it will be equal to f. Okay, for this is not for x, this is vector, right? This is for a matrix f. This is how it is denoted. So if, and here a belongs to m cross n, so it's a matrix of n cross n dimensions, then this f, or generally you have f, or I like to put Frobenius, this is equal to, this is similar to Euclidean, but it is element wise, okay, all the elements squared. So this is your sigma I equal to 1 to m. So on the rows, sigma j is equal to 1 to n. I move across the column, so I get every element, and then I'll get each element aij square, okay, aij square. And this is also equal to the trace of the matrix. Okay, so this is also equal to the trace of this matrix, A transpose A. So when you do trace of A transpose A, so this will square the matrix. It's kind of squaring the matrix, right? X transpose, if you do for vector, it will square the vector. Similarly for matrix, it is kind of, it's a covariance matrix, but it will kind of square it. So you will square, take a square root, and the trace elements will have all the elements. The trace elements means the diagonal of the matrix will have, and this, and the diagonal is only defined for square. So A transpose A will become a square matrix automatically. If this is m cross n, you know, right? So this will be m cross n, and this will be ulta. This will be n cross m, and this will be m cross n. So finally A transpose A will be equal to n cross n. So this will become a square matrix, and now the diagonal will be defined. And for trace is defined only for square matrices. So now you can have, and if you sum up all of them, you will get the Frobenius norm. Okay, so what is it? Okay, so this is your, also this is related to your, so since A transpose A has come, so from the singular value decomposition, you remember the second, so what was singular value decomposition? So any vector A can be decomposed as V transpose, and this term was your A transpose A, and this sigma will have all the singular values. And what were the singular values? They were the eigenvalues. They were the eigenvalues of A transpose A. So this sigma was a, so your sigma 1 1, sigma 2 2, like this till sigma RR, which was rank of the matrix, and rest everything was 0. It was a diagonal matrix. Okay, and these are the singular values. This is this matrix, so A transpose A, and this is your A transpose. Okay, so from this it is coming. So similarly, if you go and check my singular value decomposition video for more details, or you should know singular value decomposition already. Okay, I'll put the link in the description. So A is there. So this Frobenius norm is also written as a square root of all the singular values, sigma I square. So all the singular values of this matrix A transpose A, that V transpose. So all the eigenvalues of this, square root of eigenvalues. So these are the singular values, are square root of eigenvalues, because again this will be squared. A square, right? A transpose A square. So the square root will be like kind of reflecting the what would be the eigenvalues of the A matrix. That is the direction in which only the scaling, stretching or shrinking happens. So this is also your Frobenius norm. Okay, so let me show you that how the trace, also you can check my singular value decomposition to verify how Frobenius norm is also the summation of, okay, so this summation, okay, not one, so it is over I, right? Sigma over I, all of them summed up, So I told you that this is also equal to trace of A transpose A. So I'll quickly give you an example so that you understand how the formula is. You can do the maths already, so it is simple. Say for example, A is A11 simple, A12, A21, A22. So it will be A transpose, rows into columns, columns into rows. So this will become A11, A12, A21, A22. And now if I have A transpose A, this will be equal to, you multiply A transpose with A. Okay, so let me put them side by side. So A11, A12, A21, A22 multiplied by A11, A12, A21, A22, and this will come out to be, how do we go? This row into this column, row of the first into, row of the first into column of the second. So this is how we go. So A11 into A11 plus A21 into A21, A11 into A11, A1 square, A21 into A21, A21 square. So I will write it fastly, A11 square, A21 square. Similarly, this will be, the second one will be this into this. So A11 into A12 plus A21 into A22. Okay, and this will be this one into this one. So this will be A12 into A11 plus A22. Okay, A12 into this and A22 into this into A21, and the fourth element would be, so I'll just pull it up away a bit, and this last element would be A. Okay, so again, so this would be this 2 into this 2. So this will be A12 square plus A22 square. This is what it is. Okay, and what is the Frobenius norm of A? This will be equal to, this will be square root of all the elements, right? This is what is square all the elements from I to j. So this is A11 square, A12 square, A21 square, A22 square. This is nothing but A11 square, A12 square plus A21 square plus A22 square. And what is trace of A transpose A, sum of the diagonals. So this is equal to A11 square plus A12 square, A12 square plus A22 square. This is the sum of all the elements, just reordered. It's a bit jumbled up. So can we say this is equal to, so can we say that is equal to square root of trace of A transpose A? So this is the proof. Similarly, you can check for A transpose A and you can calculate the eigenvalues, and then you will get the singular value also. I hope this is clear. Okay, this is clear. Let's move to the next topic, that is vector induced norms. Vector induced norms. So what is vector induced? That is, if you multiply it with the vector, okay, so this is derived from all the specific vector norms. So you have a vector and a matrix. So I'm finding a norm of a matrix. So this is a way to calculate the matrix norm only. So I'm calculating matrix norm by using a vector. So that's why it's saying vector induced norms. So what does it mean? That when I multiply, okay, a matrix with a vector, so it will stretch it in certain directions. So this norm just measures the maximum stretching a matrix can apply or induce on a vector. Maximum it measures, okay, it measures maximum stretching or shrinking, okay, whatever, maximum stretching a matrix can apply or induce in a vector, because if you multiply A with V, this is a linear transformation. Direction and size both changes. Either or, both can change, or only one can change. Okay, we saw this in eigenvalue decomposition, that these are special vectors where only the size changes and the direction doesn't change, but a matrix can change both of it. So we'll see now vector induced by the vector P norm. So we know vectors P norms. So what is your matrix induced P norms? So we will see. So, and this okay, one more thing. Okay, so this measures the maximum stretching of can apply or induce in a vector where the vector has unit length. So we fix the length of the vector as unit vector so that we can just measure the stretching. So this vector's length doesn't come into play. So I just want to check how much stretching the matrix is doing. That will be the characteristic of a matrix, right? How much stretching it is doing on any vector, and that's what is here the way to measure that how much it can stretch a vector, and that is the vector induced norm. So for that we will fix the vector's size as length as 1, so that we can separate out and measure just the stretching that has been induced by the matrix. Okay, so I'll write that property here, that is where vector has unit length, okay, under whatever chosen vector norm, okay, under chosen vector norm, whatever vector norm we are choosing. Okay, so now let's see matrix induced by the vectors P norm. So we have seen vectors P norm. So for each one, so how do we write it? So we write this as the P norm for a matrix. A is a matrix where A belongs to M cross N, and this is your P norm. How do we write it? This is equal to, so there is a formula. This is your max, okay, under the norm of Pth norm is 1. Okay, so this is the max stretching we are calculating under the condition that the measure of that vector for that Pth norm, that should be 1, that should be unit vector. And then what do we measure? We measure the stretching for that Pth norm by vectors Pth norm. So this will be 1, so we'll measure the stretching here under the Pth norm. So that's what this will measure the stretching. This will measure the stretching, the magnitude of stretching. So that is also a quality of a matrix. Okay. So what will be my, similarly there will be P1 norm here. So here will be, so if like P1 norm, vector induced P1 norm, so I'm just talking about what will be P1 norm. So this will be equal to, we will write A1 like this. This will be equal to, so there is a formula for this, and then finally this will come out to be max of 1 is less than j is less than equal to n, and then you will sum all the columns and find the maximum sum column, which column has the maximum sum. This is what it gives. So this is a summation of I equal to 1 to m and absolute values of all the columns. This is equal to max absolute column sum, max absolute column sum of that matrix. For example, you know the matrix, right? So this is your A is equal to A11, A12, like this, till A1n, n columns, and here are like M1, M2, A21, like that, Mn, like this. This is your M cross n matrix. Yeah, this is your M cross n matrix. So what does this mean? You do a summation of I equal to 1 to m on Aij. So for any I, so for if I is 1, so the first one, and then you do go from 1 to m. Okay, from here 1 to m. 1 to m is happening on this side, 1 2 till m, and here on this side is 1 2 till n. So I'm varying now. So this outside is column 1 2 till n, and the inside is m. So I'm varying towards this. So this summation from here will give me the sum of this column. Okay, so I'll take the max of this. So I'll get the sum of this column, then I'll get the sum of this column, then I'll get the sum of this column, and then I'll get the sum of all these n columns, and I'll take whichever is the max out of it. So that is max absolute column sum. So out of all these column sums, whichever is max, okay, I'll get n such values, I equal to j to n. So I'll get n such columns, so n such values will be there, and I'll choose whichever is maximum, and that is your P1 norm for this matrix. Okay. Similarly, there is something called P infinity norm. Okay. P equal to, this was P equal to 1, right? P is equal to 1. Now similarly, there is P is equal to infinity. Let me go to the next page for the matrix. Okay. And this is given by A of infinity, like this, and this is just nothing but sum of the rows. Now this is the other way around. I1 is equal to less than is equal to I is less than equal to m, and then I'll go from j is equal to 1 to n. Okay, and I'll sum, then I will take the absolute value of Aij, and this will give me max absolute row sum. So same thing here, same thing here, but this P infinity now. So P1 was capturing the column sum, now I'm going row wise. So max of j equal to 1 to n Aij. So for the first row from 1 to n, I'll take this sum. This is a summation, sigma is sum. So I'll take this sum, then I will go for the next row, second till mth row. So 1 to m, for all the m rows I'll take sum like that, and I'll choose the max out of it. That's what this means. This is how we read this. Take the sum of this. This is summation. J equal to 1 to 10 Ij, fix one I, that is 1 for the first one. Then you get all this sum, then this sum, then this sum, and then you take the max for all the m rows. So this is your row max of absolute row sum. I'll give an example so that you understand. Both, it will make clear both of them. So for example, your A is equal to, so it is taking absolute values. Okay, so it will take a smaller matrix. So you have 1, minus 2 and 3, and you have 4, 5 and minus 6, say. So we have to take absolute values of each one and take row sum. So say for example, if I'm taking column sum first, so 1 plus 4 is 5, 5. Here absolute value of 2, absolute value of 5 7, and absolute value of 3 and 6 is 9. And on row size 1 plus 2 plus 3 is 6, and 4 plus 5 plus 6 is 9. So only the magnitude we are measuring. So what will be my A1 norm? This will be your max column sum. So this is your max column sum here. So this will be equal to 9. And what will be your A1? Okay, what will be your A infinity? That is your max row sum. So this is your this one. So this will also be equal to 9. Okay, sorry, this is 4 5 6, right? So this will be, sorry, this is 15. Sorry for the maths. 4 plus 5 9 plus 6. So this is 15. So this will be equal to, that's what I thought. How can both of them be 9? Okay, so this is what it means. So there's one more norm. So that is the common P is equal to 2 norm that is used. P is equal to 2 norm in this context, okay, in the vector induced. That is where vector induced only for a matrix. So this is nothing but this is called max factor, by which, so this is, I'll tell you. So the second norm is nothing but this is taking your, again, A transpose A. Okay, here you remember A transpose A was there, right? Second norm, yeah, trace of A transpose A. Similarly, here also we'll take the A transpose and then we'll get the singular values. So whatever is the max singular value for A, right? That is your P2 norm, vector induced norm for that matrix. So it will be sigma max will be the maximum singular value. And where will you get this from? Again, from the same equation. So your A can be decomposed as U sigma V transpose, and your V transpose is nothing but A transpose A, and this sigma is having these values. I drew it earlier also. Yeah, this is a sigma. So your sigma has all the values. So this first one, if you arrange it in descending order as we did in singular value, so this will be the direction of maximum variation, and that's what your A2 norm is. Check the singular value decomposition video if this is not clear. Okay, so this is the max value of this. So this is the max value by convention. Sigma 1 1 sigma 1 1 is greater than sigma 2 2 is greater than equal to, like that, till sigma R R, where R is the rank of the matrix. We have discussed this in detail. Okay, and this is also called this is also called spectral norm. It's also called spectral norm. We have discussed this in spectral decomposition also when we are doing eigenvalue decomposition. So this matrix will be a square symmetric matrix. This is square plus this will be a symmetric matrix, A transpose A. So this is square plus symmetric because this is A transpose A, kind of covariance matrix. So all the factors will be same across the diagonal. So if you take mirror images, that will be same. So this is square symmetric. From that, this thing comes that this is a spectral norm. If you don't understand the spectral decomposition, check that eigenvalue decomposition video. I'll put that link also in the description. From that, you'll understand. Okay. So the max stretching, again, this is also always measuring the max stretching. Okay, it is all these matrix, this vector norms are measuring the max stretching, and here this max stretching will be given by my sigma max, or the maximum singular value. After I do the singular value decomposition, this will be, my top one will be that, and that's what is your spectral norm or P2 norm, vector induced for a matrix. So let's do an example so that you understand. For example, my matrix is equal to 2 1 1 2. So my A transpose also will be same. This is symmetric here only. Okay, this is also only symmetric. So this will be 2 1 1 2 only. So what will be my A transpose A? This will be equal to 2 1 1 2 into 2 1 1 2. This will be equal to 2 into 2 4 plus 1 into 1 5. So this will become 5. 1 into 1 1 to 1, no, this 2 into 1, this one. Now these two will multiply these two. So 2 into 1 is 2 plus 1 into 2 is 2, so this will become 4. This symmetric, so this will also come out to be like this, so this will be your 5 4 4 5. And what are these sigma singular values? Are the eigenvalues of A transpose A. So how do we calculate eigenvalues of this? So this A transpose A, say for this is your A transpose is your C matrix, is equal to A transpose A. So my determinant of C minus lambda I is equal to 0, means 5 minus lambda 4, and then this will be 4 here, and this will be 5 minus lambda. Okay, this determinant of this is equal to 0. What will be the determinant for this? 5 minus lambda whole square is equal to 4 square, 4 into 4. So if I take, I can also write it as lambda minus 5 whole square is equal to 4 square. Implies if I take square root, lambda minus 5 is equal to absolute value plus minus 4. This implies lambda is equal to 5 plus 4, or lambda is equal to 5 minus 4 is equal to 9 or 1. So these are my eigenvalues of A transpose A. So what will be my singular value? Singular value corresponding to this will be square root of 9, that is equal to 3. So this is your sigma max equal to 3. This is equal to your P2 norm, P2 vector induced norm for matrix A. I hope this example makes it clear. Okay, so that's all for this video. That's what we had in for this. So we have done this. So let's do a quick revision. So this is about vector norms, and a norm of vector means this is a way to measure how big a vector is or how far it is from origin, and there are different ways to do this. And it is a function which maps a vector which is n-dimensional to one scalar value. It gives a vector which is n-dimensional and gives me finally a scalar value, that is its magnitude or length. Okay, and this norm, any kind of norm calculation should follow 3 rules. First of all, the norm will always be positive, and if you scale it by alpha, the vector, then the norm should also be scaled by alpha, and you should follow triangle law of inequality, means sum of 2 individual norms separately should be less than or equal to, okay, the sum of both the norms together. Both together should be less than individual. So this is a triangle law of inequality. Should follow this. Then the P norm generalized is this format. So let me highlight this and the color, and you can just change P to get other norms. So the first norm, L1 norm, is called for vector. It's called Manhattan distance. Okay, that is just the absolute value. And the L2 norm, that is the most common norm, that is Euclidean distance, where we take the square the absolute values and take a square root of that. And then we saw for a simple vector, the L1 norm, L2 norm, and the L infinity norm, that is which is the max value. And then we came to matrix norm. So there are 2 types. One is the element wise, and the second is vector induced norms. The first element wise was Frobenius norm, where we just square all the individual elements of the matrix and we take a square root of that. That is a Frobenius norm, very common. And this is also equal to your trace of the A transpose A. We also proved that and saw that. Okay, we also proved this thing. Then next was your matrix induced norm. So matrix induced norm means how much that the maximum stretching, because the matrix stretches a vector and changes its direction, right? So we are measuring what is the maximum stretching a matrix can do on a vector, and that is your vector induced norm. So via a vector we are trying to get the size of a matrix, that is the size is equivalent to the stretch that it is producing on a vector, and that measures the stretching. And the condition for that is that the unit length, that vector on which we are measuring, that should be the of unit length under the norm that is being measured. You saw that for each norm the length may vary, right? In Manhattan and Euclidean distance case, you have seen that. So the formula is given by this. Okay, this is the formula. This is the max of all the values given the condition that the length of that norm of that vector for that pth norm is equal to 1, and then we take the stretching pth norm and then we divide it by the vectors norm. Okay, and then p1 norm we saw, that is the maximum of the column sum. So we take all column sums and whatever is the maximum out of all this value, that is your p1 norm. Similarly, p infinity norm was we take all the row sums and take whichever is the max value out of this. And then we saw p2 norm, which was the maximum singular value of the A transpose A, and we take the singular value is what, that you take the eigenvalue of A transpose A and then take a square root of that, and that will give you a singular value for this matrix. And the max value, which is the top of this, that is how we arrange it. That is your singular P2 norm for vector induced, and this is also called spectral norm. That's coming from the spectral decomposition. We have discussed this in EBD. Okay, so that's all for this video. Thanks for watching this video. Have a good day and bye for now.